name's Martin. I'm the moderator for this room. This is from RDBMS to NoSQL at enterprise scale with Rick Houlihan. Rick leads the developer relations team for the strategic accounts at MongoDB. Prior to joining MongoDB, Rick was a worldwide technical leader for NoSQL services at AWS, where he led the architecture team responsible for migrating thousands of workloads from RDBMS to NoSQL. Rick brings over 30 years of technical experience to the MongoDB team and has authored 9 patents in cloud virtualization, complex event processing, root cause analysis, microprocessors architecture, and NoSQL database technology. Please welcome to the stage Rick Houlihan.
Great, thanks everybody. Thank you for taking that time out of your day to come hear me talk a little bit about NoSQL. I love NoSQL. It is a big part of my life. I've a long history in NoSQL technology. As was just mentioned, I run the developer relations for strategic accounts here at MongoDB. And are we up on the, do we have my session on the screen? There we go. And I work with our strategic accounts generally to kind of help developers get over that hump, right? How do you start to look at data in the context of a NoSQL database? Because things are a little different when you look at NoSQL, right? It's not the typical relational database that we're all used to. Again, I have a long storied history in NoSQL technology. I was previously the worldwide technical leader for NoSQL services at AWS. I ran the NoSQL Black Belt team for Amazon Retail, which managed the transition from relational technology to NoSQL and developed some of the design patterns and best practices that Amazon uses to solve these problems. And that's what we're here to talk to you a little bit about today. So as far as the agenda for today's session, we're going to talk a little bit about why Amazon made that decision. It's pretty important, why are we taking the core database that we've used for 40 years and ripping that out of the heart of our business and moving in this new technology? Obviously, an enterprise like Amazon had really good reasons for doing that. And so we're going to actually break that down because a lot of the technology decision isn't really about what works better. Decisions in technology in the enterprise scale are really made about what costs less, right? And that's really what drove those decisions. We're going to talk a little bit about that. We're going to talk about what it took for them to find that path, right? How do we get through this transition? How does an organization transition, make that kind of a technology transition? And so to do that, we're going to talk a little bit about the history of data processing because it's not the first time, right, that we're making this type of a transition. The relational database wasn't the database that we used, throughout time. We had to get there somehow. So looking at how we got there gave us some insight when we were looking at this problem as to where we needed to go and why we needed to go there. And then finally, we're going to break it down into making it work, right? How do you make this work, this new technology, right? How do I model relational data in a NoSQL database? We always talk about, you hear this term non-relational, right? Non-relational data to me does not exist. I've worked with thousands and thousands of customers now. I wouldn't say thousands and thousands, but easily hundreds, maybe over 1,000 workloads that I've had my eyes on. And I've never seen this non-relational data, right? Data, when I query the data, there's relationships. That's defined by the conditions of my query, right? Non-relational data is what's on the hard drive before you format it, right? If anything else, and every other piece of data that we are asking for has some structure to it. It has schema and it has relationships. Otherwise, we wouldn't care about it. And we're going to talk to you a little bit about how we model those relationships in a NoSQL database, because this is where developers break down most often, because intuitively, as developers, we all know our data is relational. So how do we get through this process? How do we execute that plan, right? What does that technology transformation look like at an enterprise scale, right? It's not like you can snap your fingers and it just happens, right? What was the process that we had to go through, to make all of that happen, right? So the first thing we're going to talk about is why. Why did we make this decision at Amazon to make this move? It was a huge decision to make. And I love this quote. If you guys aren't familiar with Roy Bennett, he's a motivational author. But this is a great quote, right? Change begins at the edge of your comfort zone. Okay, remember that. Because if you're comfortable with the decision you're making, then it's not about change, right? It's about doing what we've always done. And what you've always done is not going to work, right, when it comes to scale. When you look at Amazon's business in 2018, right, the Amazon retail organization was well over $200 billion. Heck, it was over $300 billion when you throw in Amazon Web Services, right, and you throw in the partner reseller network. It was a massive organization, and a lot of people think of Amazon and they think AWS and they think cloud, right? That this company, they were born in the cloud, so it must have been easy for them, but they weren't born in the cloud. It's important to understand when you look at Amazon's business, Amazon was born in 1995. Okay, in 2003, when Jeff Bezos wrote the famous missive about how we're all going to be based, everything's going to be service-oriented architecture, right? We were a $5 billion company before that became the mantra, right? So by 2005, Amazon was a $5 billion business, and it was built on monolithic stacks, okay? And those monoliths didn't go away overnight. As a matter of fact, they were still around in 2017, 2018, when we kicked off our project, our migration project, right? The big project we called Rolling Stone, right? Amazon had, thousands of Oracle instances, over 3,000 Oracle Server instances. We had over 10,000 application services. We had 25,000 global developers, right? And we were all well-versed in relational database technology. But for years, the business had known that something's broken, right? Amazon scales like nothing else. Everybody talks about Amazon scale, right? Well, I've worked Amazon scale, and it's true. It scales like nothing else. And Amazon was breaking things. They were breaking, by 2018, everything was breaking. But things were breaking in 2013, right? Amazon retail went down in 2013 for 45 minutes and cost the business $5 million. And that's actually when this process started, okay? To start to look at where did we break, how did we break, right? We broke, and when we started looking at what was breaking, right, it became obvious that the cost of the relational database was a big, big line item, right? That infrastructure was enormous. We had the largest Oracle license in the world. Okay, so we started breaking down what we're actually doing in these databases. And a couple interesting things came out, right? 70% of the access patterns that we were running against the data, 70% of those patterns were for a single row of data on a single table, all right? Another 20% were for a range of rows on a single table. So we weren't running complex queries against the data. But it was interesting was the other 10% of the ones of those access patterns were what made everything work, right? The complex patterns, right? So you can't just architect a solution for the simple patterns. You have to understand how to deal with those complex patterns. But the bottom line is this cost structure of the relational database was tremendous. And there was an interesting trend in the industry that was going on that we were noticing. It's one of the reasons why Amazon actually built its own processor, was that the CPU performance was flattening, right? In 2014, 2015, this was noticeable. And at Amazon, they're actually studying this. If you think about what happens, right, in data processing technology, data processing is about, if you look at the history of data processing, it's about a series of peaks and valleys of what I call data pressure, okay? Data pressure is the ability of the system to process the amount of data that I'm asking it to process in a reasonable cost or a reasonable time, all right? When one of those dimensions is broken, that's a technology trigger. We're going to invent things, right? We've invented many, many things over the years, okay? The first database we were all born with is a great one. It's between our ears, right? When my eyes are open, it's online, it's highly available, okay? But it's a single user system, right? Questionable durability, zero fault tolerance. We're not going to build enterprise services on that, right? So we needed to build a system to be able to store structured data, right? So storing structured data, our first system of storing structured data was ledger accounting, right? Writing things down, all right? This actually worked very, very well for many millennia until the 1880 US Census came along, and a man named Herman Hollerith was tasked with processing all of that data, right? It took him 8 years. If you're familiar with the US Census, it takes 10 years, it's a 10-year cycle. So if it took him 8 years to process in 1880, he knew in 1890 we needed to do something different, so he invented the machine-readable punch card and the punch card sorting machine, and a tiny little company called IBM was born. Important to understand IBM, they had an enormous impact on the database technology space over the next century, right? So we rapidly ran through many innovations: paper tape, magnetic tape, distributed block storage, random access file systems, hierarchical management systems. And in the 1960s, late 1960s, early 70s, a guy came along, Edgar Cod. Edgar Cod had a mission, right? Edgar Cod wanted to give people a system that allowed them to ask questions of their data without writing code. That was what Edgar Cod wanted to do. Nobody thought Edgar Cod could do this because the data model that he built, although it was beautiful, right, the normalized data model, beautiful data model, it was too expensive in CPU, right? The join cost, the time complexity of the join, nobody thought he would ever be able to deliver a commercial system that was viable because of that cost. One interesting thing came along that helped him, right? Moore's Law, right? Moore's Law balanced the checkbook for the relational database, and it did it for many, many decades. But that recently broke, and we'll take a look at that in a second. But what we're looking at now, as a result, is because the cost efficiency of the relational database is declining, right? We're looking at actually resurrecting some of the old technology we had. NoSQL databases are very, very similar to the hierarchical management systems of the late 60s, early 70s, right? Where they're optimizing the CPU cost at the cost of storage, right? Well, storage is cheap. If you look at what's happening today, Moore's law is no longer an enabler for the relational database, okay? Moore's law is actually not a law. Moore's law is an observation. It's actually a financial equation. And what it's telling us is how much is the industry willing to pay to double the transistor density every 2 years. And since 2014, what we can see from that chart on the left there, that's the top 500 supercomputing clusters around the world, right? And supercomputers invest in everything to get the most petaflops they can, right? So every innovation they can possibly throw at their clusters, they're throwing at it, and they're barely able to hit Moore's law every other year or so since 2014. So that's telling us that the industry is not willing to pay enough, okay, to double that transistor density and increase CPU performance. So what does that mean? That means per core performance is flattening. The TCO of high time complexity services is increasing, okay? And we're going to break down the time complexity of the relational database here in a second. This is the reason why I always say, look, distributed SQL is not the answer, all right, for scale. We all know that the relational database only scales vertically, and the distributed SQL is a solution that's built to try and scale horizontally, but distributed cross commits, adding time complexity to the process, this is not going to solve this problem. Okay, the only thing that solves this problem is reducing time complexity, and that's where NoSQL data modeling comes in, okay? The cost of storage is continuing to fall. It will continue to fall. The CPU performance is continuing to flatten, and it will not get any better, again, because the industry is not willing to pay to double that transistor density for a server processor. Okay, we're running 5-nanometer fab. We're running that for what? Mobile phones. Why? Because the mobile phone is a revenue-generating device. Think of the revenue that a mobile phone generates in its lifetime. A server processor doesn't generate that revenue for the manufacturer, right? There's no subscription services available for a server motherboard, right? So server processors are unlikely to get 5-nanometer fab anytime soon, and the cost of the relational database is only going to continue to increase, right? So if you're not looking at replacing that technology, and this was the equation, these are the numbers that Amazon was looking at in 2014, 2015, and seeing this trend. The writing was on the wall. It's not going to get cheaper to operate a relational database. It's only going to get more expensive, okay? So this is not new thinking, right? This is actually, these are things that Edgar Cott himself talked about when he wrote his paper on a relational model of data for large shared data banks, right? The seminal paper, the introduction of the normalized relational model. On normalization, it's an advantage for storage, right? It's an advantage for communication of bulk data between systems. On denormalization, it's going to offload your CPU. It's going to cost you more storage, right? These are concepts that were very well understood even back in the 60s and 70s when the relational database was being developed. On defining an ERD, don't overcomplicate the ERD, right? Don't join static lookup tables into every query because you're going to burn CPU when maybe denormalization is actually okay, right? Don't over-normalize your data, which I see all the time today. If you think about the extra time complexity that's happening in a relational database, and we're going to break this down in a second, but I always I hear a lot about how crypto is responsible for global warming, okay? But when you think about the time complexity of joins and the billions and billions and billions of relational database queries that execute every day, and the time complexity of those CPUs, I'm telling you, the relational database is more responsible for global warming than coal, okay? All right, so when am I going to use NoSQL? This is one of the questions we had to answer, obviously, at Amazon. It's like, it's not for everything, right? At least it wasn't for us. Although, the line is being blurred, and being blurred even more today, right? But SQL typically is a database that is agnostic to the access pattern, right? It doesn't care what questions you ask. You're going to come in, and just as Edgar Cott wanted, you can write a question in a descriptive language. You don't have to write code, although some people would tell you SQL is code. But the reality is you can theoretically ask a simple question and you can get your data, okay? It does that by being agnostic to every access pattern. It does that by being optimized for none. That's what it means, right? If I'm agnostic to every access pattern, essentially I'm optimized for nothing. I'm just going to tell you it's going to cost me something to get you any answer, but I'll get you any answer. But the reality is that the code we write is not to ask random questions, right? I have never written a piece of code that asks random questions to the database, right? When you write code, you're doing it to automate a process, to run the same query 1 billion times a day, not 100 random queries or 1,000 random queries. I don't know what they're going to be, right? I actually have to code the queries. So if you actually understand the access patterns, then you can start doing things with the data, and we're going to look at this in a second, to actually create structures that are much easier for the computer's systems to retrieve, right? For the database and do less work. And this is the key, right? We want to do less work. If you're going to reduce the cost of your data processing infrastructure and decrease the amount of infrastructure that you have deployed, the only way to do that is do less work. So OLTP processes and OLTP applications are really the sweet spot for NoSQL databases, right? This is where you're going to see the most cost efficiency because we're going to create data models that mirror your access patterns. Think of it almost like materialized views, right? Representative data structures that mirror your objects in the application layer. We'll break this down in a second. But the idea here is to be able to deliver a system that is very, very fast at the high velocity access patterns that make up the majority of your workload, all right? Now, at Amazon, the system we had to do this with was DynamoDB. It's a great system, okay? One of the problems with DynamoDB, it has no support for ad hoc queries, none. So if you needed to run complex, ad hoc aggregations, you ran that data out through, chain streams into Lambda, and you did all kinds of crazy things asynchronously. One of the nicest things about MongoDB is that you actually get that left-hand side. You get that with MongoDB. We support ad hoc queries. We have first-class support for aggregations. I think today, I'm not blowing it by saying this, the press release is out there, there's an SQL API now in front of MongoDB. So honestly, you get the power of ad hoc queries for those corner case patterns, that 10% that make the actual application work, and then you have the power of NoSQL for the common case patterns, right, where we're going to actually build the data model to reflect the way that we're accessing the data, okay? So let's talk about what it takes to make that work, right? What does it look like to model your data in a NoSQL database and manage and model those relationships? And I love this quote because I think that Mark Twain, when I read this, I said he's a time traveler, right? I mean, he's dealt with big data, right? Data is like garbage. You better know what to do with it before you collect it, right? I mean, how many problems have you seen? How many data swamps have you seen where people didn't realize what they're going to do with the data before they started putting it into something, and now all of a sudden they're paying to store it? Anyways, as we talked about before, it's all about relationships. Doesn't matter what type of application you're building, social networking, document management, process control, IT monitoring, any type of application you're building, I'm going to have some sort of ERD that describes my logical data diagram, my entities, how they're related, right? I've got to understand the data and how it's related in order to be able to model it. Otherwise, what am I doing? I'm just throwing a bunch of bits and bytes in a bucket and randomly selecting things. I mean, when you log into your bank account, you don't get some random account, right? I mean, I always get my account, unfortunately. I wish that I actually got someone else's account most of the time, but, hey, it is what it is. But, you're not going to, there's a relationship, again, always between the data, right? And these relationships typically have been kind of built into this normalized data model that we're all very familiar with. This is the third normal form for a simple product catalog. If we look at the relationships that we have one-to-one between products and books, products and albums, products and videos, right? One-to-many between albums and tracks. We have a many-to-many between videos and actors. And again, simple ERD here. We're not going to be talking about any complex queries, but you can think about what I need to do to get all the products, right? To get a list of all my products. There's 3 different queries I got to run. There's various levels of joins I have to go through. There's a many-to-many join that I have to go through a mapping table, right? And there's lots of different things going on. And so maybe what I want to do is I want to say, let's look at this data in a NoSQL database where I'm going to take those rows from those tables and I'll collapse those rows into objects. If you think about the primary access pattern of this workload, what's it going to be? Get me the product by ID. Get me all the products in a given category or with a given condition or a type or a color, right? But whenever I get the product, it's interesting because I really want all the data for the product, right? I mean, typically when I throw the product up on the window at Amazon Retail, when I look at the product, I'm seeing the description, summary of the reviews, all this data that's from those tables that are kind of joined together, right? If I put them all in one document, now I don't have to join those rows, right? I can just go ahead and say, get me product by ID. Now, this is a simple approach, and probably the simplest approach to NoSQL is simply collapse the tables. Not necessarily going to work for every workload, but it'll work for this one pretty well, right? And that's the key, is figure out what structure works for your workload, right? But if we look at what's happening from a time complexity perspective, let's put some data on those tables, right? These are now just a simple product catalog, and we're going to start joining things. So if I go and get my one-to-one join, it's not too bad, right? If I go into the one-to-manys, it starts getting worse. The time complexity just starts expanding. And anybody who's a real DBA in this room is going to look at that SQL and say, haha, last time I saw anything that simple was what, in college, DB 101, right? I mean, this is not, when you talk nested joins and outer and inner and all this kind of stuff that's going on in these crazy SQL statements you see on these servers, you can imagine what the time complexity calculation looks like, right? That's your CPU. That's your CPU burning away, assembling data across tables, okay? And it doesn't help to be in a distributed SQL, a single box SQL, whatever. If you're running a relational data model and you're joining tables, right, that's a problem, okay? So if you think about what happens when we actually model those joins, right? In NoSQL, we start to look at, first we'll look at that key value kind of lookup, right, where we have a product blob, okay? But what's going to be interesting here, we're going to talk about later, is there's this thing inside of these blobs that I've got this array called target, right? That target array is actually what am I related to? So this object might have the metadata, describes the product, everything I need when I get product by ID, but there's all kinds of other access patterns that I'm going to want to be able to support. We'll go through those in a second. But what's interesting here is that now that I'm using these embedded documents, I don't have time complexity. It's all an index lookup, right? So log in. It never gets worse. It doesn't matter one-to-one, one-to-many, many-to-many, right? As long as it's just to get the document, it's just an index lookup, right? And that's great. But like I said, there's a lot more that goes into an application than just the simple lookup. So we said 70% of our access patterns at Amazon were for a single row of data, 20% for a range of rows from a single table. This pattern might actually work well for that, but what happens to the other ones? Get me all the books that were written by a given author, or get me all the people that are related to X, right? So let's talk about adding more dimensions, right? Let's throw some more documents into this collection. What do we got now? We've got other actors that were in those movies. We've got the director of the movie. I've got the song documents, right, that describe how those songs are related to other entities in this collection, right? We've got maybe the writers, the producers, the artists that the song that performed the song. We've got all the albums the song was on, right? And now if I actually index the target array, and this is one of the best things about MongoDB and document databases, multi-key arrays, okay? What I can do on the index now is I can create essentially a B-tree lookup structure of those target IDs. And what have I done? If you look at this structure, I've joined all of those documents on those dimensions, right? So now I can select where target ID is Mary Shelley and get everything that she's related to, the books, the people, the critiques that were written about her work, whatever, right? Where the target ID is a song name, I'm going to get all the information about the song and all of the pointers to all the documents that are related to that song, right? And so essentially what I've done is I've used the index as a join mechanism, okay? And this is a critical learning in NoSQL, right? When we were at AWS and going through these problems, I had so many teams coming to me and telling me NoSQL doesn't work, okay? DynamoDB doesn't work because it's too expensive, all right? Because I have to run multiple queries, things are too slow. If I have to join at the application layer, that's ridiculous, okay? So the key thing here was being able to understand that if I index documents that are stored in the same table or same collection on a common dimension that has a shared value, essentially I've eliminated the need to join that same index across that same value across multiple tables, okay? That's what the relational database does. If you think about it, that's exactly what it does. You don't want to be joining unindexed columns, right, in a relational database. That's going to cause you a lot of overhead. You want to index those attributes. You want to put pointers to your parent objects and your child tables, and you want to join on those IDs. Okay, well, I've replaced that process by putting all those objects in a single table and indexing on the ID. Okay, and what I've done is eliminated the time complexity. As you can see here, it's like querying doesn't matter, one-to-one, one-to-many, many-to-many. If all those documents share the same table and they're indexed on a common attribute, the time complexity is O log n, okay? And I have so many examples of services at AWS that we built that we would create these index structures like this to join those documents into the index, store everything on one table. There's so many examples of teams that they couldn't have done it any other way, right? Because the cost is wrapped up in that time complexity, all right? The cost of your infrastructure, how much infrastructure do I need? 70% of the overhead of handling a request for a database is marshaling the request. It's not getting the data. Okay, it's managing the connection, it's handling the request, it's marshaling the data and shoving it back across the TCP/IP stack. Okay, so if I can eliminate the one request from a transaction, I'm going to reduce the overhead of that transaction. So if you think about the idea of overloading your documents into a single collection, this is what we call the polymorphic design pattern, right? I mean, MongoDB's had this design pattern for many, many years, all right? What I'm bringing to the table here is a different spin on this. We're saying it's polymorphic, but we're also, if you're familiar with MongoDB patterns, there's a pattern called extended reference, right? And that extended reference is about building these arrays, these target arrays, these pointers, right? How do I relate this document to the other documents that it is related to? How do I track those relationships? Today, a lot of people might tell you these documents belong in different collections. What I'll tell you is if you do that, then you might as well go back to using a relational database because you're going to increase the time complexity of your high-velocity queries. You want your high-frequency queries to be joining data in a single collection. Now, do I always want data in one collection? Heck no. Okay, I mean, it all depends on the workload. It depends on the data lifecycle. It depends on the access patterns. What I can tell you is that if you have a common access pattern, a high-velocity access pattern that is accessing documents of multiple types that are related to each other, they probably belong in one collection. Documents that are data that is accessed together should be stored together. And that is the mantra that we've always espoused at MongoDB, right? So whether you use an embedded document, whether you use multiple documents, that's also another choice that we could get into here. I'm not going to talk too much about that. There is a point at which this structure becomes overly complicated, and an embedded document is a better choice. And I would advise you to go. There's several sessions here today about data modeling and design patterns and whatnot. They talk about these trade-offs, right? One of the fundamental concepts of modeling in NoSQL is design of the access pattern. Right, so we need to understand that before we start doing any of this stuff. What I'm showing you here is just an interesting way to express relationships in a NoSQL database. All right, so executing the plan, how did we do it? So one of the things that we learned real quick at Amazon was that you got to learn how to use the technology before you try to use it. Okay, and this is a great chart to kind of explain that. When everybody knows how to use something, right, that's when that early majority's already arrived or we're past the early majority. And then when everybody knows how to use it, we have really good results, right? Like today, everybody knows how to use the relational database. I wouldn't say everybody, but you know, based on the SQL that I've actually written myself, I probably don't know how to use it too well, but that's okay. I don't write SQL anymore, so I don't break things. But the bottom line is when you learn how to use new technologies, you have better result. And that's what this chart tells you. In the beginning, we've got those innovators running around. They've developed something new. We've had the technology trigger, right? That's data pressure. It's either too fast or it's too slow or it's too expensive. And we're going to go invent something. And those people had good results. They tell everybody else, look what I found. Those people come running to that solution and they have miserable experiences. Why? Because they didn't bother to figure out how it works first, and they don't have the skills, okay? And this is what we had at Amazon. So many teams running down the path of NoSQL, it's got to be NoSQL. That was the mantra, right? Rolling Stone, we're moving everything to NoSQL. And having terrible experiences and coming back and saying it's too slow, it's too expensive, right? As we started to get that skill set distributed through the organization, we started having better results, okay? And this is the experience that any organization is going to see. And the way we did that is exactly what I'm doing with our customers today. This is what my team does. We ran a program at AWS. We called it NoSQL Day. We brought the teams in. We would have deep dive sessions where we'd talk about, you know, the technology, the kind of, you call them brown bags, right? But the real meat here was understanding that workshops, they're okay. Brown bags, they're okay. But when a developer leaves the room, if he hasn't solved his problem, then he's going to be just as lost in trying to figure out how this works. So at Amazon, what really worked for us really well, and I actually translated that program to AWS customers, I brought it to MongoDB, is to use your own workloads, right, as that learning experience. My team consists of data modeling experts. We sit down with our customers, we break down their workloads, we talk about their access patterns, right? We say, here's how you might model this solution, and we give you a prototype of a data model when we leave, and hopefully enough of a breadcrumb trail that you can follow it yourself, right? Developers are really smart, right? Developers can look at documentation and figure out APIs and syntax and all that. They don't need me to show them that. What they need me to show them is how do I solve my problem with your technology? Right? And that's what my team does. This is what we did. This is the program we built at Amazon. It was tremendously effective. We launched a global program. We went across all of our development centers. And the other key learning here was understanding that you're not going to win every battle, okay? Don't worry about it if your development team says, ooh, I don't like that, okay? Let those developers go ahead and have their own experience. When your developers who have good experiences and win, right, they're eventually going to move off to other teams. They'll bring that experience with them, and the DNA will replicate. Right? This is what we saw at Amazon, right? Once we stopped trying to use a hammer to get teams to actually do it, Instead, we used the carrots, and we showed them how to solve their problems. Eventually, the teams that resisted it ended up converting after a year or two when they got enough developers from other teams that were saying, why are you doing it this way? We did it so much easier with service X, right? So start a program like this of evangelism and training, but use your own workloads, right, as that tool, as that workshop, right? Sandbox environments are great to a certain extent, but nothing beats using your own problem to solve a problem with a piece of technology. That's how you learn how it works, right, as a developer. If you're interested in running one of these sessions with someone, with my team or with our SAs, feel free to reach out to your account reps. They can get you connected. All right, so that's what I've got for you today. Hopefully this was a good session. I've got a lot more content about data modeling and whatnot, but they only gave me a half hour to talk, so I could talk for another hour or two if you wanted me to. But anyways, thanks a lot. I appreciate it.